So welcome to today's class. Last week we looked at various issues, and our concluding remarks were that an ideal test is the one where type 1 error and type 2 error are actually minimized. But the problem is that type 1 error and type 2 error are known to be inversely related. So as you try to minimize one of the errors, then the other error goes up. So that kind of problem will be answered by what we call the Neyman-Pearson lemma, which is our starting point in today's class. Okay, so and we are saying that under the best tests is that the classical approach to finding a good test, you start by fixing the level of significance. And as we mentioned earlier on, is that the level of significance or the probability of making type 1 error is under the control of the researcher or the statistician. So you have the privilege of fixing the alpha or the level of significance in advance. And the most widely used level of significance in hypothesis testing is alpha is equal to 5%. Okay, so this is referred as the default level of significance. The default level of significance. So in an exam setting, if you are not given the level of significance, you are supposed to use alpha is 5%. There are other levels of significance that can also be used. For instance, you can have alpha is 1%. You can also have alpha is 10%. But in an exam setting, you only use these two when you are told to use the same. Okay, so what you do is that after you fix the level of significance, you try to search for a test that minimizes type 2 error. So you can use simulation to get different values of different candidate values of H1. Then you plug them into the likelihood, and then you see the value of beta that you're going to obtain. And then from there, you can also get, you can calculate the power of that test. Then through that process, you are likely to get a value of the alternative hypothesis that gives you the highest power, that gives you the highest power of the test. And that is what we are calling the most powerful test. And we're saying that the key result in that search is what we are actually calling the Neyman-Pearson lemma, which provides the best test in the case of two simple hypotheses. Two simple hypotheses, for instance, when you have H0 that mu is equal to mu naught, and then you have H1 that mu is equal to mu1. In simple hypotheses like that is when you are able to do that. Then we are saying that for a given level of significance, the critical region and of course the test statistic for the best test is determined by setting an upper bound on the likelihood ratio L0 of L1. So this upper bound we are setting is like the threshold that we are setting is like the amount of evidence that we need so as to be able to reject H0. And when we talk about L0 over L1, for instance, in the example that we looked at above, where we were considering an exponential distribution, f of x given lambda is equal to lambda e minus lambda of x, when x is bigger or equal to 0. L0 is the value of the likelihood when H1 is true. And H1 was defined like this: mu is equal to 20, which means that lambda is 1 out of 20. So the value of this expression, the value of that expression when lambda, when H0 is true is what we shall be calling L0. So in our case here, L0 will be 1 out of 20. Then E raised to power minus X divided by 20. That's the value of L0. Then using the same logic, you can get the value of L1. That is the likelihood of this function, but now when H1 is true. And H1 was defined like this. H1 is that mu is equal to 30. H1 is that mu is equal to 30. So this means that lambda is 1 out of 30. So our L1 will be 1 out of 30 multiplied by e raised to power minus x out of 30. So when we talk about the likelihood ratio, we just be dividing this number with this number. We divide those two to get the likelihood ratio. So we reject the null hypothesis if that ratio does not exceed some critical value, which will be determined, of course, by the level of significance which has already been set in advance. Okay, so this is the illustration there of what we have just done. The Neyman-Pearson test rejects the null hypothesis. So that's the ruler. The null hypothesis, when the likelihood under H naught, that is what we have done here, divided by the likelihood under H1 is less than some critical value. And this critical value is always determined by alpha, which you set in advance. Then you are told, example 3, show that the test that we did earlier on in example 1 is a Neyman-Pearson test. You show that it is a Neyman-Pearson test. So you just need to work with these two values. With these two values, you get their quotient. I think that example has been solved here. So you will have 1 out of 20, e raised to power minus x out of 20, divided by 1 out of 30, e raised to power minus x out of 30. Is less than some constant. You reject the null hypothesis when that is less than some constant, which will be determined, or which has been determined. So you notice that you can play around with these coefficients. You take them to the right hand side. So you'll be left with e raised to power minus x out of 20 divided by e raised to power minus x out of 30. It's still less than some constant. If you take this constant to this side, we still remain with some constant. Okay. So simplifying on the left hand side, this is what we have. When you simplify these, you see these are simplification of something like this. Let me see. If you have x power n divided by x power m, we know this is the same as x. You know that bit, huh? So using the same logic here, when you simplify the left-hand side, you'll be left with this. You'll be left with that, which is less than some constant. We don't care about the value of the constant at the moment. Okay, so when you have e raised to power minus x over 60 is less than, let's say, let me call it k, constant. Remember, we are looking for this x. We can make x the subject of the formula here by taking natural logarithms both sides. You take natural logarithm both sides. So you'll be left with x over 60, sorry, is equal to ln of k, is equal to ln of k, is equal to ln of k, is equal to ln of k. So where you can just say that, there's a minus and this is less than not equal. Then that is let me repeat that story. Let me repeat that story so that there's no confusion. So we are saying that on the left-hand side, you will be left with e raised to power minus x over 60 is less than some constant. So if you introduce logarithms, natural logarithms both sides, you'll be left with minus x over 60 is less than some ln of k. You can make x the subject of the formula by multiplying both sides by minus 60. So that means that x will be, now it becomes greater than minus 60 ln of k. Okay, where you can just say this is the same as x is bigger than some constant if you don't care so much about the value here. So x is bigger than some constant. And if you remember, we were rejecting the null hypothesis. Let me take you up there. We were rejecting the null hypothesis. Where is that example? We were rejecting the null hypothesis when x is bigger than 28 here. We were rejecting the null hypothesis when x was bigger than some constant, and specifically the constant here was 28. So this is what we said. If the value is less than 28, we fail to reject, or we reject when otherwise. We reject H naught when otherwise. So that just agrees with what the question was all about, or what that test was all about. Because when we are rejecting the null hypothesis, when x was larger than some constant. In our case, that constant was specifically 28. So that is enough proof that the test that we have conducted there was a Neyman-Pearson test. That is enough proof that the test that we've just concluded up there in example 1 was a Neyman-Pearson test. Okay. Then now I want us to look at the generalization of the Neyman-Pearson lemma. And we're starting by saying that in most of the cases, you will have the null hypothesis and either a one-sided or a two-sided alternative hypothesis. And we're saying that it is only in certain special cases, that a single test is available. So that tells you that there are some cases where we do not have the best test or is not available, okay? So that best test is what we are calling the uniformly most powerful test, which is true for all the parameter values. Like if you simulated mu, like the one we did up there where we simulated mu from 10, let's say to 1000. If you simulate all those values as potential values of mu1, then if you're able to get a single test which is true for all the values of mu, then you have the uniformly most powerful test. But that does not happen in all the cases. So there are cases where that kind of test is not possible, especially when we have two-sided tests. When you have two-sided tests, you are not likely to have that kind of test. So in such cases, you generalize the Neyman-Pearson lemma into another test, which is called the likelihood ratio test. The likelihood ratio test. So the likelihood ratio test is very similar to what we have just seen there, but now we use the maximum likelihood instead of just the likelihood. So we have a ratio of maximum likelihood when the null hypothesis is true, and the maximum likelihood for all the possible values that mu can take. So we're saying that the max LO is the maximum value of the likelihood L under the restriction imposed by the null hypothesis. So when null hypothesis is true, you just plug in the parameters there. And then max L is the overall maximum value of L for all the allowable values of all the parameters involved, This kind of test is usually quite useful in modeling, especially when you want to decide between one model and the other one. Usually, if you have two models which seem to be doing almost the same job or are doing equally good, and then one of them happens to be shorter than the other one, if the models are nested, if there's something called nested models, if the models are nested, then in other words, if one model is a subset of the other model, you can regard the shorter model as your null model. And then you can have the longer model as your alternative model, okay? So you will test the hypothesis to see whether you need to keep the longer model, whether it is worthwhile keeping the longer model, or you better go for the longer model. That's a question about parsimony, because usually we prefer models which have very few parameters. If a model has fewer parameters and is doing the same job a longer model is doing, you are required to use the shorter model. That's what we call, you prefer the shorter model on the basis of parsimony. So maybe this will come out very strongly when you be doing some modeling, when you be choosing between one model and the other one under the concept of parsimony. So we're saying that in the most common cases, when H0 and H1 are together, when H0 and H1 together cover all the possible values of the parameters, this generalized test rejects. So we reject the null hypothesis if this ratio is true. We reject the null hypothesis if the maximum likelihood under H0 divided by the maximum likelihood under all the possible values of the parameter in question is less than some critical value. Of course, this critical value is always determined in advance by the significance level that has been assumed. And of course, that also depends on the distribution that is being considered. And we are saying that important results include cases where the sampling is done from a normal distribution. As you saw in the previous example, we're using an exponential distribution. You can use any other distribution, but important results only come when you are working with a normal distribution. As you know, normal distribution is one of the most important distributions. So a normal distribution with mean, mu, and variance given by that. Or in symbols, we can write it like that. So that's the situation when we are going to have very nice results under the likelihood ratio test, okay? So because when sigma squared is unknown, if sigma squared or the variance is not known, the test, the most powerful test that we're talking about now is called the t-test. Is called the t-test, and it's defined by this, the t-test, where of course x bar is the sample mean. Then mu naught is the hypothetical population mean. So this is a value that you find in the hypothesis. This is a value. For instance, we had mu naught was 20 in the above example. Okay. Then we have S. Of course, S is the sample standard deviation. S is the sample standard deviation. That explains why we are using T distribution, because sigma is not known. And then of course, N is the size of the sample, Okay, so when sigma squared is not known, we use a T distribution with the given degrees of freedom. We use a T distribution with the given degrees of freedom. Okay. What is the name of the divisor? What is the value of the denominator? Sorry, what is the name given to the denominator here? What is S over root N? Which name do we give to that value? S over root N. It's called what? This is called the standard error. Okay, that's the standard error of x bar given by S over root N. Okay, so we use a T distribution. We use a T statistic, is the best statistic in this case. But if sigma squared is known, if we know sigma squared, that means we are not going to use S here. If you know sigma squared, you will not use S, but you'll use the same formula. But now the best test there will be a Z test. Will be a Z test or the standard normal test. So which is given by this x bar mu naught, but now over sigma over root N, which is normal with mean 0 and variance 1. So that's the basic distinction between when to use a T and when to use a normal distribution. Simply is based on whether sigma is known or is not known. Okay, so that is it. So you need to notice that there are some other when the sample size is very small. When the sample size is very small, when n is less than 30, of course you need to adjust how you calculate your S. You need to adjust how you calculate your S. So in that case, when n is small, you use S is given by, you can say summation of x minus x bar squared divided by n minus 1. This is when n is less than 30. But if n is larger than 30, then you don't need to subtract 1 here. You don't need to subtract 1 there. You can just divide by n. You can calculate the standard deviation by just taking the sum of the squared deviations divided by n. That's something you need to note somewhere, okay? But we are not going to those details. Now, another important result that you get is this one. Another important result that you get when normality is assumed is you can also get this kind of test, which is a chi-square distribution with 1 degree of freedom. I guess some of you know that when you square the z, variable, you always end up with a chi-square. You always end up with a chi-square with 1 degree of freedom. You end up with a chi-square with 1 degree of freedom. So when normality is assumed, you can also get this kind of test as your best test, which follows a chi-square distribution with n minus 1 degrees of freedom. And this test will be used to test equality of variance or to test hypotheses revolving around variances. Maybe I forgot to mention that this kind of test will be for mean. These two will be used in the context of testing hypothesis for the mean. The T, and so this formula here is used in the context of testing hypothesis. Yeah, I think I wrote it here. Hypotheses are about the mean. You use that kind of statistic, okay? Or you can use now the one given here. Of course, this S squared here is the sample variance. The numerator there is the sample variance. And then the divisor here is the hypothetical hypothetical population variance. Is the hypothetical population variance. So the hypothetical value is the one that you will find in the definition of hypothesis. So like you can see, our null hypothesis here is that sigma squared is equal to sigma squared naught. So that's the hypothetical value. So you are checking the ratio. You are just checking the ratio of those two variances. Okay. Of course, you want to prove that the ratio is bigger than 1. Okay. So in the background, we are checking that the ratio is different from 1. Okay. Where the null hypothesis will be that you can write this in other words. You can write this null hypothesis in other words, that sigma squared over sigma 1 is equal to 1. So we're trying to prove that this is not true because when they are equal, it means that the ratio is equal to 1. Okay. So those are some of what you call the best tests. We've just looked at, we've just mentioned 3 of them. The t-test, when normality is assumed, the t-test, the z-test, and also the chi-square test there, because we have seen that a chi-square, or maybe you know that a chi-square is obtainable from a normal distribution, from a standard normal distribution. So next, I want us to look at p-values. P-values, okay? The p-values are much more informative than some of the tests that we have mentioned up there. Okay, in testing of hypotheses, actually, p-values are more preferred than the other things that we mentioned up there, because p-values, when you use p-values, you get to know how much evidence are you relying upon to reject the null hypothesis. In the previous cases, you just collect evidence, and once you pass the threshold, you either reject the null hypothesis or you fail to reject. But you don't say how much evidence do you really have against this null hypothesis. So the p-values, we have the advantage of knowing how much evidence do we really have of rejecting the null hypothesis or otherwise. So we started by saying that under the classical approach, with a fixed predetermined value of level of significance, a test will produce a decision as to whether or not to reject a null hypothesis. Okay, but merely comparing the observed test statistic with some critical value and coming up with a conclusion like this, because you'll always end up with a conclusion like this. Once you do the test statistic, which is always calculated, then you compare with the critical value, you say either you're going to reject the null hypothesis at 5% level of significance, or you can say, I'm going to fail to reject the null hypothesis at the 5% level of significance. Or you can say, I reject the null hypothesis at, let's say, 1% level of significance. But you see, we are saying that kind of results does not provide the reader or the user of that information with detailed information on the strength of the evidence that you are using to reject the null hypothesis. How strong is the evidence that you are relying upon? Because here you either reject or fail to reject. You don't say how much evidence you have, okay? So we're saying that a more informative approach is to calculate and quote the p-value. The p-value is usually called, in long, it is a probability value. P-value is just a probability value, okay? So you calculate a p-value of the observed statistic, okay? You calculate a p-value or probability value of the test statistic. Maybe that's not clear, but you can say that when we talk about a p-value, let me speak in layman's language, is the amount of evidence in probability terms now, is the amount of evidence that you have in support of the null hypothesis. The amount of evidence that you have in support of the null hypothesis, okay? So for instance, so as we know, a probability value is a number, a probability is a number between 0 and 1. So this is increasing evidence. This is increasing evidence in support of H0. Okay, and this is decreasing evidence. This is decreasing evidence of supporting H0. Okay, so it means that when the probability value is very low here, is very close to 0, you have very small evidence to support the null hypothesis. And when there is very small evidence, it means that you are going to reject the null hypothesis. If you have no evidence to support your null hypothesis, it means that you're going to reject it. So in a nutshell, when we talk about p-values, the rule is very simple. The rule is very simple. So this means that you reject H naught. When the p-value is very close to 0, you reject H naught. In other words, we say you reject H naught. Sometimes we just say for small p-values. You reject H naught for small p-values. Then on the other hand, if your p-value is large, and the word large, okay, even the word small here is in quotes. Huh? The word small here depends on your alpha. For instance, if you're working with alpha is 5%, which is the same as 0.05. If your p-value is less than this value, if your p-value is less than this value of 0.05, you have no evidence to continue holding onto the null hypothesis. So you reject the null hypothesis. But if your p-value is bigger than 0.05 and you're using alpha is equal to 5%, it means that you have evidence to keep the null hypothesis or to fail to reject the null hypothesis. Any value which is bigger than 0.5. Okay, so that's the basic rule. So if your alpha is, let's say, 1%, if that is the level of significance that you've already predetermined, because we said that alpha is always determined in advance. So once you get your test statistic, you calculate the p-value. So if your p-value, for instance, is 0.05, and we're using alpha as this, which is 0.001, like that, then it means that your p-value is large. As far as this one is concerned, you have a large p-value. That means that you have strong evidence in support of the null hypothesis. That means you should fail to reject the null hypothesis, or you should just accept the null hypothesis. So that's the basic rule of the p-value. It is just the amount of evidence you have in support of the null hypothesis. And this evidence is given in terms of a probability. And that probability is what we are calling a p-value. Okay? So that's basically it about the p-value. I may not want to go to the other stories, but you can read them. You can read them as shown there. Okay. So we're also saying that the p-value is the lowest level at which H naught can be rejected. The lowest level at which H naught can be rejected, and so on and so forth. Example. We have an example here. When testing the hypothesis that theta is 0.5 versus the alternative that theta is 0.4, where theta is the probability of a coin coming up heads. So this is a binomial scenario, a coin coming up heads, and 82 heads have been observed in 200 tosses. The p-value of the result is given by, I've shown how the calculation is done. But it's good for us to understand that this is a binomial scenario where x, the variable of interest or the success outcome is the number of heads. Okay, so we can claim that x is a binomial variable, and for binomial, what do you need to know for binomial to be fully defined? There are two things that you must know for binomial to be fully defined. For us to fully define this distribution, what do we need to know here? There are two things that you must know for the binomial distribution to be fully defined. That is n and p. So n is the number of trials here, which is 200. And then p is the probability of success, 0.5. So as you know, we can approximate the binomial distribution. Using the normal distribution. And we know for the normal distribution to be fully defined, we need these two things. So we can redefine this variable x. We convert it from a binomial distribution to, or from a binomial variable to a normal variable. So we need mu. And how do we get mu? Mu for the binomial distribution, mu is given by n times p. The mean is given by n times p, which is 200 times 0.5, which is 100. And then we need sigma squared, which is the variance. And variance of a binomial variable is given by npq. The standard deviation is given by sigma, which is the square root of that. So this will be given by, what's the variance in this case? It is 200 times 0.5 times 0.5, which happens to be what? Which happens to be 50. That's the variance. So now we can define this variable as a normal distribution, okay? But now we need to adjust something, because as we know, binomial is a discrete distribution. So if you want to approximate it using the normal distribution, which is a continuous distribution, we have to make some adjustment on the value of x. We have to make some adjustment on the value of x using what we call the continuity correction factor. Continuity correction factor. Continuity correction factor. So that's why you see now we are not using, okay, this is the initial problem. That x is binomial with a mean, with 200 trials, and p, the probability of success, is 0.5. Okay, so when you look at it from this perspective, so let's try to sketch the distribution so that we know the kind of hypothesis that we are looking at, the kind of probability we are looking at. So if I convert it to a normal distribution, we'll have that kind of shape. Then the mean will always be here, which is 100. And then I'm talking about the number of successes that were observed were 82. So 82 is on the lower side. On the lower side. 82 is on the lower side. So when we talk about the p-value, the p-value in question here is the shaded area. That's why I said this. It is the lowest level of significance at which H naught can be rejected, the shaded part. So that is your alpha, which is, sorry, that's our p-value. Let me call it p. It's a level of significance, but I call it p-value. This is our p-value. That's our p-value. This is 82, not 28. 82. So I need the area below 82. The area below 82. That's why I've given this statement like this. Probably that x is less or equal to 82 in the context of binomial, which now we can switch to normal distribution after adding the continuity correction factor, which is represented by 0.5. Which is represented by 0.5. So we are now going to work with probability that z is less than. Now we find the corresponding value of z when x is 82.5. For continuity, we switch from 82 to 82.5. Then we compute the corresponding z statistic from there. The corresponding z statistic using x is 82.5. As you know, the definition, z is given by x minus your mu naught divided by s, or sigma, whichever is available, okay? Or square root of s squared. I don't need to do that. So already we have seen that this is a normal distribution with mean equal to that, and sigma squared is that. Sigma squared is that. So we need to take, so we can call this one sigma. So this will be 82.5 minus our mu naught. Our mu naught, which is our mean, which is our mean value, which is how much? Which is 100. We got it from here. Our mu is this guy, which is 100, divided by square root of 50. So you compute the Z corresponding to those values of X, okay? And that is what is given here. You get we are looking for a Z which is less than, if you simplify, you'll get that. We are looking for a Z which is less than minus 2.4, okay? So this is what we have done. So these were values of X. So if you switch to standard normal distribution, you'll be having 0 there. If this is your Z. So we're looking at this value here. So instead of this is X is equal to 82, now we have a Z value which is minus 2.47, whatever, like that. So this is what we're calling the P value, or the lowest level of significance at which we can reject H naught. Okay. So you can use tables, you can use normal tables to find the area on the left-hand side, or the shaded area. You can use normal distribution tables, or you can use R to quickly compute those probability values. I'll show you how to use the tables. I think many of you know how to do it. So let me display the normal distribution tables. And we are working with minus 2.47 something. Yeah? So the normal distribution tables, let me display that.
Hello, sir.
Yes, yes.
Sorry for the interruption, but it seems that some of our brothers are stuck there in the waiting room.
In the waiting room. Good. I've allowed them in.
Yeah.
Thanks for that. So let me display the normal distribution table. This is one version of the normal distribution table. I don't know which one we are used to, but this one way where this is giving half of the table, half from 0 going up, the positive values, or then negative values from 0 going up. Then the values given in the table here are represented by the shaded part. So it will give you the area from 0 to a certain Z value there. There are other different types of tables. I know you've come across them. Okay. So for instance, if you have a Z value of, for instance, if I pick a Z value of 1.50, if I put here 1.50, then the area given here, 0.4322, is the area between, is a probability that Z is greater than 0, less than 1.5. The area from 0 to 1.5, that's what is equal to 0.4322. That means if I need an area, probability that Z is bigger than 1.5, it means that I use the complement, because the table will give me from 0 to 1.5. Then I know from 0 to infinity, to positive infinity, that is a 0.5 of the area. So this will be given by 0.5 minus 0.4332. The area above Z being 1.5 is given by that. So basically that's what we are going to do. And because you know that the normal distribution is symmetric, we can map the values on the positive side on the negative side. So we shall be using the values as if we are working on the positive side, even when we are on the negative side. So here in our problem, we have a value of minus 2 points. This one will be an approximation now, because the tables are giving up to only 2 decimal places. Minus 2, I'll say minus 2.48. So I'll work with minus 2.48. So this is the area I'm talking about. So you know that area is equivalent to the area from 0 to 2.48. It is equivalent, but now on the upper side. So the tables that I'm displaying here will give me the area from 0 to that point, which is the same as from here up to that point. So for me to get the remaining area, I need to take away from 0.5. So 2.48 is this much, which is 0.4934. So this is 0.4934. The unshaded part from here up to here is that area. But my objective is to get this, so that will be 0.5 minus 0.4934. So if you do that simple math, you will get this is 0.4934. So you get the area is the p-value in this case will be 0.00666. So if you use the tables, you'll get something like that. Okay, but you have the option of using your computer now that you know a little bit of programming, and when you write this code should give you the answer within just a simple line of code. It will give you the p-value. It will give you the p-value. So I should have said that these ones are from R. This is the R code. So basically what we have done, the R code, usually this R code, p-norm, gives you the cumulative probabilities from -infinity up to a given point that you are looking for. So this code here gives you from -infinity all the way to -2.47 etc. So that R code gives you that probability. If it was an upper tail test and you want to use R code, if it was an upper tail test like this, where this value is 2.474 like that, if you want to use R code to get this p-value here, or that probability value, you will take 1 minus, and you say p-norm 2.47 etc. So this part here will give you the cumulative probabilities all the way from -infinity up to this point. So if you want the remaining, the upper area, you take 1 minus, you use the complement rule. So you can play around with that code and get different values and so on and so forth. So basically that's the p-value. So this is the evidence that we have in support of the null hypothesis. This probability value here, 0.0066 etc. is the evidence that we have in favor or in support of the null hypothesis. So to know whether this evidence is large enough or small enough, you must have the threshold, and the threshold is determined by alpha. What is our alpha? So because in this question we are not told the level of alpha, if alpha is 5%, if we set it at 5%, then you compare this probability value or p-value with this value 0.05. Then using those two comparisons, you will say whether the p-value is small or is not small. So whether to say a p-value is small or not depends on the level of significance that has been adopted. So if we use alpha is 0.05, clearly the evidence that we have here, 0.006, is very small. So when the evidence is that small, it means that you reject the null hypothesis. You reject the null hypothesis. And that means that the test is significant. That's all you say, yeah? The test is significant. If you fail to reject the null hypothesis, you say that the test is not significant. The test is not significant. Okay, so basically that is it. So if you're using alpha is 1%, the story will change, okay? Or if you're using alpha is 0.1%, for instance, because you can also use that. If your alpha is 0.1%, then clearly this p-value here will not be small, and the test in this context will not be significant. Will not be significant. So that's just the basic rule of how the p-value is applied in hypothesis testing. So what have we said here? We said that the observed p-value, that is 0.006 whatever, means that H0 is very unlikely to be true. Very unlikely to be true, because you have very small evidence in support of it, with a probability less than, this value here is less than, if you round it off, will be less than 0.01, with a probability of less than 0.01 of H0 being true. In other words, we have very strong evidence against the null hypothesis. We have very strong evidence against this hypothesis. And this hypothesis here claims that the coin is fair. This means it's a fair coin. The null hypothesis claims that it's a fair coin. That is, the probability of getting head is equal to the probability of getting a tail, which is half. So there is so much evidence against that hypothesis. And that means that we conclude that the coin is biased against heads. The coin is biased against heads. As you can see here, the probability of head here is less than 0.5, or is 0.4, sorry. So that means there's bias. There's bias against the heads. So basically that's how you use p-value to make such kind of decisions, okay? And I've told you here to repeat that example. When you change the value of x from 82 to use 95, if the number of heads observed there was 95, or when it was 120, what will happen? Maybe you can do together when x is 120, we see what will happen. So what will change there? The z statistic. So when x is 120, we are going to have your z. So this is what will happen. This is what will happen. And it's good for you to, the sketch is always good. The sketch adds a lot of value. So this is our mu, which was 100. The mean is 100. Now we're talking about 120. 120 is on the upper side. Remember the other one was 82. That's why we were looking for the lower probability. So now here we have 120. So we're looking at that. So possibly if we are working at 120, then this value should be something like beta is 0.6 or something like that. Something like that. So the alternative hypothesis will change if the number of successes observed is more than 100. Okay, so like in this case, now we expect a different alternative hypothesis. Okay, but now that will not affect what we're going to do here. So we are looking at the probability that x is bigger than 120, which is equivalent to probability that z is bigger than, so we find the value of z, which corresponds to this value of x. And because we are switching from discrete to continuous, we need to adjust for the continuity. So we shall work with 120.5. Our mean is 100 divided by square root of 50. So we're looking at that probability. Okay. So this diagram here represents that. So if you simplify that, 120, so somebody can simplify that. 120.5 minus 100 divided by square root of 50, which is probability that z is bigger than 2.89, 899 etc. I hope you are getting that. Please try to do it in the on your side. So that means using the standard normal distribution, we have something like this. If this is our mu, which is 0, we have 2.899 etc. So we're looking at that probability. That's a p-value. The p-value. And again, we can use our R code. You can use our R code to get that p-value. So this is a value. So let me do this here. Let me calculate those values from here. So our Z value is 120.5 minus 100 divided by square root of 50. So this is our new test statistic. So we have this. So that's our new Z. So what is the value of Z in this case? We are getting, something has not happened. Okay, there's a bracket which is missing somewhere. You guys, do you know how to use R? Yeah, 2.8998991. So this is our Z statistic. So you want to compute the p-value corresponding to that value, which will be given by 1. So the p-value will be 1 minus p norm when you have this value here. That will be your p-value. Sometimes you can, if you want to get everything at once, you put brackets like that. So the p-value is 0.0018 something. Okay, so the p-value is this number here. The p-value is there. So that's our p-value, 0.00187. Huh? So that is the evidence that you have in support of a null hypothesis. So that means if you had chosen an alpha of 5%, it means that you have very little evidence, very small evidence in support of the null hypothesis. That means that you reject the null hypothesis and that the test will be significant. The test will be significant.
Excuse me, sir.
Yes, yes.
Yeah, they said you've assigned it 120.5 minus 1,000 or minus 100.
Ah, sorry. Yeah, correct. This is 100. Huh? This is 100. It's 100. Sorry, I'm sorry about that. So I hope things will change. So that's our Z, and then our p-value. Our p-value. So why has it not changed? So let me run this code. So, oh, sorry, I think I did it in the background. Huh? I don't know how it happened. Huh? So, but what are you getting as the value of Z? What is the value of Z according to you from that side? 2.899 something, isn't it? Is that so?
Yes.
I know if I put 1,000 there, I should be getting a different answer. I don't know how that zero came in. Huh? Yeah, I think I had done it. I just put this Z after running the code. Huh? So I think the zero came in after I had run the code. So Z is 2.899 and the corresponding p-value is 0.0018, which is a very small evidence in support of the null hypothesis. So we have a significant test. So if you use this code, like in the case where I told you to use a 95, if I replace this one with a 95, then we see what happens. What p-value are we going to get? You will get the Z value becomes this. This is your Z value. So if you put it here, if you put this guy here, sorry, I should not have used this. Huh? I should have put here 95.5. If I work with 95.5, then I run the code. The Z value is minus 0.63. Yeah? If you have, if you're working with 95 success outcomes, then let's see how much evidence you have to reject the null hypothesis. So if you paste that guy there and you run this, you will find that your p-value will be 0.7377, which is very close to 1, because the p-values will range from 0 to 1. That is very strong evidence in support of the null hypothesis. That means you do not have any evidence to reject the null hypothesis. And if you're not rejecting the null hypothesis, that says, in the language of the problem, that says that we are saying that if you are not rejecting, which statement here? If you are not rejecting this statement, it means that the coin that you have tossed is a fair coin. If you don't reject the null hypothesis, it means that you are working with a fair coin. So that's the other interpretation. So you can try different values of X and see the different conclusions, okay? And see different conclusions. All right, so I think we should move on. Let's move on. So we have example 5 here. Suppose the critical value of 28 from example 1 is replaced by a constant K. Okay, so that the test used is we fail to reject H0 when the value of X is less than K, or otherwise you reject H0. The question is, what is the value of K that gives a test of size 5%. What is the value of K? In other words, what is the value of X that will give you an alpha or a p-value of 5%? Okay, so let's recall that example. That was exponential distribution. And this is how you can sketch it. Looks like something like that. So remember, we had a cutoff point here, which was 28. This is 0 all the way to infinity. So what we're saying here, suppose you replace this guy here with another number here, an unknown value, K. And then you want to make this size of the test, which is alpha, 5%. So if you keep the shaded part here at 5%, then what is the value of K that corresponds to that? What is the value of K that corresponds to that? Okay, what do you think? Mathematically, we're talking about if the integral from K to infinity of lambda e minus lambda of x dx is equal to 0.05, that's 5%. We're looking for that. We're looking for a K that will give us that. Of course, here we're talking about when h naught is true. So here we're going to use lambda is 1 over 120. So we're talking about lambda is 1 out of 120. This is K to infinity. Then e minus x over 20 like that. Then dx. When you integrate that, what do you get? Somebody to integrate that and tell us the value. Is equal to, this one should be equal to 0.05. Which value of K will give us 0.5? Somebody to do a quick integration and tell us. So when you integrate that, what do you get? Before you substitute, you will get minus e raised to power x over 20. Then you have values ranging from K to infinity, which is equal to, which is equal to, I want to keep 0.5 on the other side, is equal to that. So when you substitute values of K and infinity, you will get, I want to put the minus outside. There's a minus here. I put the minus outside. When I substitute infinity, I'll end up with 0. Is that correct? Because I'll be having 1 minus e over something to do with infinity, which is 0. Then minus, when I substitute K, I'll end up with e minus K over 20, like that. Which is the same as saying 0.05 is equal to this negative here, and this negative becomes a plus. So we have e minus K over 20. So we have 0.05 is equal to e raised to power minus K over 20, minus K over 20. And that's what we have down here in the solutions. That's what has been solved here. So that's what we have, which is 0.05. Remember, we're looking for K, so you can make K the subject of the formula by taking logarithm both sides, natural logarithm. So you're going to have ln of 0.05 on the left-hand side is equal to, when you take ln on the other side, you'll be left with minus K over 20. When you take ln on the right-hand side, you'll end up with that. So if you make K the subject of the formula, you'll end up with K is equal to minus 20 ln of 0.05. We'll end up with this. K is equal to that, minus 20 ln of 0.05, which is 59.91465. 465. So that means if you want, let me sketch again, if you want your p-value or your alpha to be 5%, if you want your p-value to be 0.05, then this is what we're going to have. Then this is how the distribution will look like. You will have a distribution that looks like that. Okay, so this is 59.9145. That is what will give you exactly an alpha of 5% or p-value of 0.05. Okay. Then alternatively, you can get that value, this value here using R, using the Q function, Q of exponent, Q of exponential distribution. And you just need to say, because this QX will give you the cumulative, probabilities from 0 to a given value, or 0 to a given point. So these are cumulative probabilities, and you are looking for the area shaded in green now. This one should be the QX. The QX will always give you that probability. This is what will give you by Q. Then you write there. So in our case, it should be 0.95. Then you write now the rate parameter. That is your value of lambda is your rate. So that's what I've specified here, 1 out of 120. So the value of X, or the quantile that corresponds to that, is the same with what we got using the mathematical approach. So you can use R to get that very quickly. Okay. So for the same question, we also asked to find the probability of type 2 error. The probability of type 2 error. So now with this new value of X, the threshold, and now that we have already fixed our alpha at 5%, what is type 2 error in this case? And as we said earlier, is that the probability of type 2 or type 2 error is the probability of failing to reject or accepting H0 when it is actually false. So for this kind of distribution, we're talking about a scenario like this, where this is the threshold point, this is 59.9 whatever. So we are looking at this probability, the probability of falling in the unshaded part. So this is what we're calling beta, the probability of being in the unshaded part. So clearly we need the cumulative probability from 0 all the way to 59.991 or 9 whatever. Okay, so that one has already been done. So you have type 2 error, you cumulate your probabilities from 0 to k. But now, very important to note is that you do this when H0 is not true, when the null hypothesis is not true, or when H1 is true. We can put it like that, when H1 is true. And remember, our H1 is that mu is equal to 30. So that means our parameter of interest is 1 out of 30. So that's why the PDF has changed. The constant here has changed to 1 out of 30. This is when H0 is not true. In other words, when H1 is true. When H1 is true. So when you do the integration, you will end up with this probability value, 0.8642 something. Okay. You can also get that probability using an R code, PX, where you give the quantile or the value of X, the cutoff point, and the rate is 1 over 30, and you'll get exactly the same thing. You'll get exactly the same thing. Okay, so basically that is it. That is a bit that I wanted us to cover in today's class. The p-values are quite important, and also the likelihood ratio tests are also very important. So you are very much advised to note those two concepts.